Okay, welcome to our seminar series. Today we are really glad to have Professor Ravikumar from Carnegie Mellon. Professor Ravikumar is an expert in machine learning. So I just checked Google Scholar webpage. He has 20 or 30 NIPS paper. That's the top paper for artificial intelligence. And I checked his website. He has a graduate PhD student and now become the tenure-track professor at the top 10 or top 20 university in the US. So I think he's doing a lot of amazing research. And today he will be talking about explainable artificial intelligence while representative points. Let's welcome.
So thanks to the organizers for inviting me. So today I'm going to talk about explainable AI. So AI is all in the news these days about solving difficult human games that we thought really required intelligence that was inherently human. Right? Of course, AI systems beat chess a long time back, but then there were games like Go that people never thought AI systems could beat humans. And now you have AI systems that are achieving superhuman performance in not just games, but in a lot of interesting applications. So the question that now people are starting to face is that, hey, AI systems seem to be so great, so let's start using them in society. Right? So somehow AI systems became so powerful before people are using them in society, so now people want to use these in society. And before doing so, they first want to understand, from a layperson's perspective, what these AI systems are doing. Okay? So that seems like a pretty reasonable thing to do. So let's say you get an assistant, right? And you want to put this assistant in charge of, let's say, your store. You want to be able to trust this assistant. You want to be able to see how this assistant thinks, right? And that's a similar thing people want to get from AI systems. When they want to deploy these AI systems, they want to understand how do these AI systems think. And so that's really what this talk is about. Okay, so we want to understand, so we are going to take it for granted that AI systems are able to think, not just with respect to human level performance, but superhuman level performance for very, very specialized tasks. But we want to understand how they think. So let's look at a pretty prototypical example that for whatever reason people in machine learning are super excited about, which is to look at cat images and try to predict if it's a cat or not. One of the things, that's one of the most important things for machine learners. And for tasks like these, AI systems are able to achieve superhuman performance. So this is something that I realized even with some of the really difficult examples. You can't really tell if it's a cat or not a cat. There are some really tiny dogs that, with low resolution, it's very difficult to tell if it's a cat or not a cat. And AI systems are able to. So they are able to achieve, even on this very simple task, superhuman performance. And the main way in which they are able to do so is by exceedingly complex models, which are deep neural network models. And these deep neural network models have millions to hundreds of millions of parameters. So the way you describe these models is essentially using 100 million real numbers. So that's obviously no way for us to convey to a layperson, right? Here are these 100 million numbers. This is what the network is, how it's thinking. That's no use, right? So how do we break this down a little bit? And so this is the AI black box issue, which is why does the AI system think this is a cat, right? So if I ask you, why do you think this is a cat? This is a simple example, right? You would say, okay, maybe you can see whiskers. I don't know if you can see the whiskers, but there are certain features about this animal in this image. First of all, there is an animal in this image, right? And so you have certain features that you say, and then you say, because of all these things that I see in the image, this is a cat, right? So you give an explanation for why you think this is a cat. And we want similar explanations to be generated, auto-generated by the AI system, right? The key thing is that even the experts who develop these machine learning models, who train these deep neural network models with 100 million parameters, they do not understand why the AI system thinks this is a cat. Okay? So they don't really understand. I mean, we understand it from a very abstract perspective that we are fitting something to be able to achieve low prediction error for this particular task and so on, but I don't know for this specific image why the AI system thought this was a cat. Okay. So what do we do? But before that, it's worthwhile asking, what is wrong with black box systems? Right? Complicated systems are all around us, right? Especially with the division of labor in modern complex societies. So there are lots of complex systems that we do not understand and we are completely happy about, right? So for instance, we don't exactly know how to construct a projector, for instance. Or I flew from here to here from Pittsburgh. Do we really understand? I know that many of you are from aerospace, so maybe you do understand it to a greater degree, but then again, I know some high-level physics, but I don't really understand it to a much higher degree of specificity, how this airplane is bringing me from Pittsburgh to here, right? But I'm still okay with it, right? I'm okay sitting in a metal tube 30,000 feet in the air, even though I do not completely understand it. So given that humans are okay with these essentially black box systems that are complex and that are high stakes, why do I need to explain this cat model, which doesn't seem to be that pressing, right? Again, there are many reasons. I touched upon a few, but since we are scientists, innate curiosity is a valid reason, right? I have this superhuman system that's playing games, that's classifying cats or dogs, and I want to understand how it's thinking, right? So innate curiosity, but also, I touched upon this, I might want to know how the machine is thinking if I want to be able to trust the system, right? And you need to be able to trust the system if you are a person in charge and you're going to deploy the system and you would be accountable for what the system does, right? So this happens, for instance, in the army, but across, I think, companies as well. So in an army, if a commander has people below them, right, they are actually responsible for the people below them. So if the people below them make some mistakes, then the commander is responsible. Okay? And so the main reason they are actually okay with this, so they call this chain of command, right? The reason they are okay with this is that they're able to trust the people below them. And the trust that they in turn would trust the people below them and so on. Right? But how do you trust the people below you? Right? So this seems like an inherently human endeavor, but we want to extend this to AI systems. If I'm going to use AI systems, and I'm the CFO, right, I want to be able to trust the system. But this is a problem, right? Like I said, even experts do not understand it. So with respect to the aeroplanes, the reason I'm okay with it is because I know that there are some aerospace engineers who understand it, right? So I can delegate the worry of understanding this complex system to somebody else who does understand it to a great degree of specificity, right? But in these AI systems, even machine learning scientists and engineers do not understand why it works. And so that's what makes people worry, right? So if an army commander wants to deploy the system, right, they want assurances from us that I understand the AI system, but I don't understand the AI system. I cannot give that assurance, right? And so that is another layer of caveats why we actually need to do work to try to understand these complex machine learning systems. Another reason is that knowing how an AI system works can allow us to improve it. Okay? And so this is something we see when we teach students, and even in interacting in everyday life. So the moment we understand how a person thinks, and if there's something wrong in the way they are approaching the problem, then you can say, hey, there's something wrong in the way you're viewing this problem, this is how you should look at it instead, right? And so this could be a wonderful way for us to improve AI systems, and for a layperson to improve the AI system, right? So if the AI system says, this is a cat because I can see horns, even a layperson can say, hey, AI system, cats don't have horns. And the AI system can be like, oh, okay, that's interesting, let me now incorporate it into my system. So this would allow even lay people to debug complex AI systems, right? But increasingly, it's out of our hands. The EU has gone ahead and legislated a right for explanation. So if a company is going to use private individual information in their AI system that would decide on something that would affect that individual. So let's say I'm a bank and I'm going to use your private information to decide whether to give you a loan or not, and it's going to adversely affect you. You have a right to explanation. You can say, hey bank, tell me why I was denied the loan. In case the bank was actually using an AI system. Okay. So again, it's out of hands. We have to, if people using AI systems have to explain how the AI systems work, right? So there are two main types of explanations: feature-based explanations and sample-based explanations. So there are some other types of explanations as well that are much more ad hoc, right? I can always have English text or some images, right, to explain an AI system. But these are the most rigorous approaches to explain an AI system. So let me go over how they look like. So in feature-based explanations, so let's look at this example. So now I have a dog detector instead of a cat detector. So I have this dog on the left, a feature-based explanation. So the way AI systems work in trying to predict whether this is a dog or not is that they take this entire image as essentially a feature vector. Okay, it's a vector of numbers, and what are the numbers here? Those are the pixel intensities, okay, of the image. And so those are my features, and then the AI system sits on top of that, digests it, and predicts if it's a dog or not. And so feature-based explanations say what are the parts of the input that the model thinks are important in arriving at its decision. Okay? And so here is an example where the model is saying, okay, given this image, it's the pixels in the middle that are actually important in the model having arrived at its decision. Okay. So similarly, if I'm an AI system that's deciding if somebody should get a loan or not, I can look at some key important features. So let's say this person had a very low income and they were asking for a loan of $1 million, right? Then I would say, okay, it's that particular feature that's most important in the AI system having arrived at its decision. I would say that the income was the key feature, right? So that would be a feature-based explanation. And in the case of images, this is again a feature-based explanation. It's the portion of the image that the AI system thought was most critical in arriving at its decision. Right? And there are many, many ways in which I can come up with what are the important features. And of course, the question of what are the important features for a system is a much broader question, right? So in various engineering communities, this falls under sensitivity analysis, for instance, right? So we have a complex system with a whole bunch of inputs, right? You may do sensitivity analysis to find out which are the important inputs, right, for a particular test point. Right. And the most popular feature-based explanations, primarily because of scalability, are based on gradients and variance of gradients. There's a lot of work on various ways in which to do gradients for non-differentiable models. But broadly, the way they the high-level thinking is that I have a model, and if I change the value of some feature, right, how would the model output change? This is essentially a sensitivity question, right? And so performing such sensitivity analysis per feature, I would be able to extract some notion of feature importance. And then I would just say, I would be able to sort all the feature importances and say, okay, these are the most important features. Okay? And gradients, of course, give you that, as well as variance of gradients that people use. And there are smoother variants of gradients as well. So those are one kind of explanations. The other kind of explanations are sample-based explanations. So here is an example on the left, which is a grizzly bear image, right? And here the goal of the AI system is to predict the category of the animal in the image, right? So it is able to successfully predict the animal as grizzly bear. And so on the right, you have the influential training images in the training data set that were most influential for the model in arriving at its decision. Okay? And so here you can talk about positively influential as well as negatively influential. Right? So positively influential would be examples potentially of polar bears, right? Where having seen those images would have resulted in this model being more likely to predict this particular test image as a grizzly bear, right? And negatively influential training images are images that in some sense would have discouraged you potentially from predicting this as a grizzly bear. So here you can see that the negative images are slightly confusing, right? Things that look like grizzly bears but are actually something different, while the positively influential are things that are grizzly bears and are diverse set of grizzly bears that would be able to help the model to arrive at a model of a grizzly bear. Right? And so this is something we do to humans. Right? So let's say you go up to somebody who is extremely distinguished, right? And so this is something that interviewers do a lot. They would say, okay, what were some of the books that most influenced your way of thinking, right? So this is a question that gets asked a lot. What were some books or what were some movies and so on that influenced your thinking a lot? That's this question. It's a sample-based explanation for how that human is thinking, right? Because if we can imagine that those books or movies and so on were the ones that trained the human in arriving at their way of thinking, similarly here, these images are explicitly images in the training data, and they influence the model in arriving at its decision. So the most popular approach to do so, to arrive at the most influential training images, are based on influence functions, which is a Best Paper Award a couple of years back at ICML. And so the way it comes up with the most important training images is again based on some notion of sensitivity analysis. So the question is asked is that, okay, so I have a whole bunch of training data, you feed it to a learning algorithm and out pops a deep neural network, right? So what if I change the weight of one particular training data point infinitesimally, right? So imagine that I upweight it. So I say that, hey, this training image is slightly more important. Pay more attention to it, right? And so then the model output would obviously change, right? So I would get a slightly different model, which would incur a slightly different prediction error. So then I can say, for what training example would such upweighting result in the most change in prediction error? Right? So those are obviously the most influential training samples. And so that's one way in which I can come up with the most influential training samples. So what we do falls under the second camp, which is we provide sample-based explanations. So there are not a lot of approaches for sample-based explanations because there is a huge scalability issue. You want something that works really fast because the training data are typically very large, right? So let's say I have 1 billion training data points, right? And the models are also typically very large, right? So I don't want to do a lot of experiments with individual training data points, retrain a whole different model, and then see what happens. This is exceedingly expensive, right? You don't want to train 1 billion deep neural networks, right? That's too expensive. So that's the main reason why performing sensitivity analysis on training data is much trickier, right? And so part of the innovation in this earlier paper was in doing this scalably. And so what we do is something that goes beyond sensitivity analysis, okay? So what we do is we decompose a neural network output into contributions from each of the training data points. So if I have 10 training data points, I say that the neural network output, as complicated as it is, right, is really a sum of contributions from each of these 10 data points. Okay. And so this then allows me to say which training data points are important, right? I just look at the contributions, and whichever training data points have large contributions, those are the influential training data points. So if there is a way for me to come up with this decomposition, then all is great, right? All I need to do is sort the contributions, right? And I can also talk about positive contributions and negative contributions. So the positive contributions, or rather the training data points that make the positive contributions, I'm going to call them excitatory representatives. Okay. In some sense, what they do is that they encourage the model to make prediction for a particular class. Okay, so all of these are with respect to one particular class. Okay, so even if you have a multi-class prediction problem where, let's say, I have 1,000 animals, I'm going to focus on the prediction of one particular class, let's say dog, right? And then I can talk about excitatory representers, which would encourage the network to predict a dog. Okay? And similarly, I can talk about inhibitory points, which would discourage the network from predicting a dog. Some training data points would, again, have positive influences for that class. Some training data points and negative influences for some class. And again, this is just based on the contributions. I don't need to do a really expensive sensitivity analysis, which just does not scale. Right? So before doing that, let me just give you a 3-slide overview of deep neural networks, which many of you, I'm sure, already know, but let me just to set up, I guess, the notation and so on. So again, this is, deep neural networks is all about stacking a whole bunch of sigmoid units or variants of sigmoid units. So what is a sigmoid unit? It's the box at the bottom. You have a weighted linear combination of inputs. Okay? Take a weighted linear combination of inputs, and then you apply some nonlinearity, which classically was the sigmoid, which you can, but essentially its purpose is like a thresholding function. So if this weighted linear combination is larger than some threshold, I will fire 1. If it's smaller than some threshold, I will fire 0. But the sigmoid is a continuous variable. Okay? And these days we don't use sigmoids, we just use things like ReLU, but those are just details, right? So essentially you have these sigmoid-like units, which are a weighted linear combination and some nonlinearity. Now that, if I just have a single sigmoid unit, that's just logistic regression. On the left is the input, on the right is the output, and if I can fit these weights, that's logistic regression. What deep neural networks are, is that they stack these sigmoid units in many, many layers, right? Where each layer consists of multiple neurons, what they call neurons, which in turn is essentially one sigmoid unit of all the neurons in the previous layer. Right? And so I can keep stacking this till I get to the final output layer. Right? That's it. It's just a whole bunch of stacking of sigmoid or sigmoid-like units. And so these are deep architectures. So where, again, these are essentially just neural networks, except that you have many, many more layers. Right? So part of the reason why people were excited about these deep neural networks, and when I say people, I mean both people within machine learning as well as people without, outside machine learning, is that this seems very similar, at least to some level of caricature, to how humans think, or how our neural architectures are structured. Right? It's very hierarchical. At the bottom layer, right, is essentially a representation of the, let's just look at a visual cortex, for instance. Right? So at the very bottom layer is essentially a very low-level representation of the image. Again, if it's imagine that it's just a set of, if it's a grayscale image, it's just a set of pixel intensities. Right? It's just a vector, a very long vector. Right? It's 100 by 100 pixel. That's 10,000 pixel intensities, right? And so pixel intensities are very, very unstructured, and they have very little semantic connotation to humans. Right? It's just one number, like 23 in that top left. It doesn't really tell you much, except that that's great. Right? But then you can combine these to get higher and higher level representations that are more and more semantically meaningful to humans. Right? So I can combine these low-level pixels to get things like edges. Right? You can combine edges to get things that are, intersections of edges. Right? Then you can start getting closed objects. Right? And then finally you can get to even higher level abstract concepts like sitting, right? Or happy, and so on. So that's, to do so though, each high-level representation depends on the concepts in the layer below it. And if you were able to construct such a thing by painstakingly specifying these, that's great. But the magic of these deep neural networks is that it's automatically able to get these just by fitting this multi-layered sigmoid unit structure. Okay, so that's that. So this is in contrast with shallow learning architectures. So what is a shallow learner? So contrasting deep learning with shallow learning. So in shallow learning, you have the inputs x1 through xn. Again, think of these as pixel intensities, right? Instead of a hierarchy of layers, you just have a single layer. You go from the input x, x1 through xn, to the output y. That's it, right? You don't have multiple layers of semantic representation. And the way it works, at least the kernel variant of these, is that you do not just take a weighted linear combination of the input to arrive at the output. What you do is something as given in that expression, which is that the function is essentially described by a contribution from each training data point, right? And where that contribution from the training data point depends on the similarity k, where this k is a similarity function, between the test point x and the training data point xi. And so that's it. So these are essentially kernel methods which you can essentially think of them as soft nearest neighbor, right? So I'm going to predict what movie you like by looking at the neighbors close to you, right? And what movies they like. But how do I define what's close to you? That's specified by the function k. Okay? So the function k allows me to quantify the nearness of the training data points xi to you, the test point x. Okay? So these were shallow learning methods, which are to be contrasted with the deep neural architectures, right? And these are shallow again because there's just one layer going from x to the output y. So what we did was to actually come up with a representative theorem for deep neural networks, where even though you had these hierarchical architecture for deep neural networks, we were able to actually provide such a representative theorem where the output of the neural network is again a sum of contributions, one per training data point. Okay, so here is a little bit of notation. Y hat I is a prediction of the neural network. Okay, xi is the input. Think of it as an image, a cat image, right? And y hat I would be whether it's a cat or not, right? 0 or 1, let's say, right? Or some continuous variant of it. Okay? Something between 0 and 1, something closer to 1 means that it's more likely to be a cat, right? So phi is essentially the output of the previous layer, right? The final layer, right? And you then take these final layer before the nonlinear activation, apply the nonlinear activation, and then you get the final output, right? And so what we show is that this pre-activation outputs phi are essentially given by a linear combination of contributions. And these linear contributions again have this very natural kernel-like form, which is, again, xt is a test data point, right? I'm giving you some test image, right? And I want to understand the output of the neural network for that test image xt. And what I'm saying is that that's actually a sum of the training data points, I equals 1 through n, of this kernel function, which is a similarity between the test image xt and the training image xi. Okay? And then you have some weights alpha I. And specifically, if you unpack this kernel function, it looks like this. It's some constant alpha I that just depends on the training image, and the similarity between the test image and the training image given by that dot product. Okay, so essentially, this is again not that surprising. The neural network is essentially learning some notion of similarity of images. And then once it learns this notion of similarity, it's doing soft nearest neighbor. Okay? So that's what this representative theorem is saying. So the neural network, all these levels of architecture, is learning this similarity function. And that specific similarity function is what is given in that bottom line. And so this is very useful for us. So if you are able to, if I give you this neural network, if you are able to compute what these alpha i's and ft and fi's are, then that's all you need, right? Now, given a new test image xt, you would be able to find out these contributions of each of the n training data points to the neural network prediction for the test point xt, right? So let's unpack this a little bit. So again, with these typical neural networks for multi-class classification, so let's say capital C is the number of classes. So let's say there are 1,000 classes, 1,000 different types of animals. Then I can focus on the neural network score for one particular class, let's say dog, right? And so again, this is what you would get. The pre-activation output of the neural network is this linear combination, weighted linear combination, right? And the weight of the training data point, I, you have this constant alpha IC, where again C is the class, and then you have the similarity between the training data point I and the test point T, okay? So those are the contributions, and these contributions can be large only if two things, for these contributions to be large, two things have to occur, right? So alpha IC has to be large in absolute value, right? Because if that's 0, then the ith training data point has no contribution to the neural network output at this test point, right? And then the dot product ft to fi has to be large. What that means is that the test point xt has to be similar to the test point xi. So the neural network, so let's say I come up with an image of a chair, and if an image of an airplane has no similarity to the image of a chair, the neural network is essentially, and if I had an image of an airplane in my training data set, the neural network's output for this particular image is not going to involve any contribution from that airplane image. Okay? And so that's what it says. And what I call positive representers would be where xt is similar to xi, and alpha IC is a large positive value, and negative representers are xt are again similar to xi, and alpha IC is largely negative. Those are the most interesting training data points, right? You have training data points that look very similar to the test image, but they have a different label. This is very interesting, right? And the neural network, part of the reason why it's so successful is that it's carrying around, and you can think of the negative representers as a maximally confusing training data points, right? So especially for fine-grained classification like cats versus dogs, there are some cases that are very confusing, right? Like Pomeranians, for instance. They are nice and fluffy, maybe they look like a cat to some people, right? And so it would be a negative representative for the cat class. So the neural network carries around this knowledge that these training images are maximally confusing for the cat class, right? And so if I get an image that looks very, very close to a Pomeranian, it knows, this is not a cat, right? This is definitely not a cat, because in my training image, here was this thing that told me that this is not a cat, right? And so that's part of the power of deep neural networks, which is carrying around these confusing data points. So let's look at an example of these positive and negative represented points. And you can see that it'll give you a lot of insight as to how things work, how a neural network works. So on the left, top left, is a rhinoceros image. The neural network is able to predict that the animal in this image is a rhinoceros. Okay? The top row are the positive representers, and the bottom row are the negative representers. So again, if you look at the top row, those are all rhinos, okay, and which are similar to the test image. So it's as if the neural network is saying, okay, given this test image, let me go look at my training data point to see which images are similar to this rhino, right? And the top row are images that are similar to the rhino and are actually labeled as rhino in the training data. And the bottom row are images that are similar to the rhino and are not rhinos. Okay? So the neural network then looks at all of these and then arrives at a considered decision as to whether this is a rhino or not. And this considered decision is exactly specified by a weighted linear combination. That's it. So that's what a neural network is actually doing. Okay? And really, most of the power of training of deep neural networks is really coming from this inhibitory training examples. And successful teachers also try to do this, right? They try to find these boundary examples so that to drive learning. And if you look at some other approaches like influence functions, they don't provide that much insight, right? So if you look at the influence functions approach that people are using, that's the stuff on the right of the dotted line. It's just a whole bunch of images of cows that it's not really giving me much insight as to why that should affect the neural network's prediction that this is a rhinoceros. Okay. So that's one issue with the previous methods. So in particular, given the fact that these negative representers are the maximally confusing training images or data, right? I can actually use this for debugging a data set. So here is this experiment that we did. Okay? So neural networks, one of the problems with neural networks is that they don't really work very well when the data is exceedingly noisy. And the data has a lot of gross errors, okay, corrections. So here is an example, here is an experiment that we did. We took a training data set, and this was a binary classification problem, let's say cat versus dog. And we took 40% of the data randomly and flipped the class label. Okay, so if it's a cat, we said it's a dog. If it's a dog, we said it's a cat. And then we gave this corrupted data set to the neural network training algorithm. So obviously, the performance is not going to be that good. So on the left, you have this plot. On the x-axis is the fraction of data. Okay, so before that, I should talk about what we then did. The experiment was about, can I use explanations to find out what data points are corrupted? Right? So let's say you don't check any data, then you are at the extreme left of the x-axis, and the accuracy that you get is around 55%. Okay? So for cat versus dog, neural networks are able to achieve superhuman performance, so you should be able to get closer to 100%. Right? So 55% means that something is wrong with the data, right? So the question was, can I use explanations to figure out what's wrong with the data, right? And so one way to do that is to look at maximally confusing training data points and see what's going on. And focusing on the maximally confusing training data points, you can see that, hey, these are images of cats that are labeled as dogs. You can then flip those, right? And so this is what we did. And then on the x-axis, again, the fraction of data that we actually checked in terms of looking, essentially all we did was just sort the training data points with respect to their contributions and just looked at a fraction and then of the negative representer points and just flipped their labels. And so you can see that as I can flip more and more, as I can check more and more of the training data, the red curve actually shows how much the accuracy improves. Right? So you go up to 65% accuracy, which is still not that perfect, but still this was a completely automated way for me to improve the training data set. And this was a very difficult case where 40% of the data, essentially almost half of the data, was misleadingly corrupted. Right? And these negative representer points are exactly able to figure out what's going on and what's wrong. So we also compared it to just randomly flipping labels and using influence functions, and our approach was strictly better. So of course this was a little bit abstract. So let me look at a concrete example that shows again why negative representer points are able to debug what's wrong with the data set. Right? So here again on the left hand side is an image of an antelope. Okay? But the neural network predicts it as deer. So these are examples where I think you can see why these neural networks are able to achieve superhuman performance. To me, it still looks like a deer, but apparently it's an antelope, right? So that's a mistake, right? So if I'm a zoologist, I'll be super upset, and I want to understand why the neural network made this mistake. Right? I gave you so many training data points, and why did you make this mistake on this exam? Right? So on the other 4 images are the negative representer points. Again, these are the examples that are maximally confusing in the sense that they are very similar to the test image, but in the training data, they have a label that is different from antelope. And you can see that all of them actually have antelopes in them. Right? So they have zebra and some antelopes, you have elephants and some antelopes. And if you look at the training data label, it's actually the other animal. Right? So the neural network is seeing small antelopes and some other animals, right? But then the training data is saying, no, that's not an antelope, it's the other animal. So the neural network is saying, whenever I see small antelope, it's not an antelope, right? And so that's exactly what has happened on the left-hand side. And so this gives you a lot of insight as to why the neural network is thinking this is not an antelope, because the training data is telling it that it's not an antelope. So this is again a very standard data set, animals as attributes, using one of the state-of-the-art deep neural network models, and we are able to get this insight that you wouldn't have gotten otherwise as to why the neural network is making the decisions that it's making, right? And so how do you fix this? So one thing you can do is just fix the training data, right? You can say that perhaps remove these confusing examples where there are multiple animals and yet you're picking one animal, right? So that's confusing to the model. The other thing you can do is instead of multi-class prediction, you can do multi-label prediction, where instead of just predicting one class, you can predict multiple classes. Right? So instead of saying that it's just an elephant in that picture, you can say it's an elephant and antelope. So both of these are choices, but these choices are eliminated just by deploying this explanation on this AI system. You can also debug the feature explanations themselves. So the approach that we had was to decompose the model prediction, right, in terms of the contributions from each of the training data points, right? And so here, again, I can, given a test image, right, I can use a feature-based explanation to find out what are the portions of the image that the model is focusing on, and I can decompose that in terms of contributions from each of the test image, right? And so that in turn would give you an insight as to, so for instance here, if I use a feature-based explanation to understand why the model is saying that it's a zebra, you can see that the feature-based explanation is essentially just looking at a small portion of the zebra. Just the head and the neck is enough for it to figure out that this is a zebra, right? But then you can say, okay, what were the training data points that resulted in the model just focusing on the head and the neck, right? And so that would essentially decompose the feature explanation into contributions from all the training data points, and then that in turn would give you a lot of insight that there were these exceedingly tiny zebra images where if the model had to predict that this was a zebra, it had to focus on essentially the head and the neck. And that's essentially might be some insight you would get. And the other important thing, of course, is that it has to be scalable for large-scale data sets, and our approach is much more scalable than existing approaches. So on the right-hand side, again, is our approach in terms of the computation that it takes. So there's some initial fine-tuning, so let's just forget about that fine-tuning. So we take around 0.1 seconds, whereas to do an influence function approach takes much longer. Right? So it's essentially, there's no way you could get real-time explanations using an influence function, which again is like performing sensitivity analysis in a training data set, which is very expensive. The other problem with influence functions is that they are not numerically stable. So again, on the left-hand side, you have the values provided by essentially the numerical values of the contributions of the training data points. Okay, And so these contributions are roughly between 0 and 1. Okay? So that's very good in the sense that I can say if contribution closer to 1 means that there's a heavy contribution closer to 0 means that there's not much contribution. But if I do stuff like influence functions, the values are exceedingly small, right? So there are things like you have some values that are 10 to the minus 4 and so on, but then you have some other values that are 10 to the minus 40 and so on. So when you're sorting these exceedingly small values, that makes me worry a little bit, right? And so that's why we came up, that's why you get these examples that we had a few slides back where there was a rhino, but then I sort the influences of the training data, I get cows, right? So that's mainly because of these numerical instability issues. So just to summarize, explainable AI is a big open challenge. It's now an emerging subfield in artificial intelligence, where the main goal is to take these complex black box AI systems and explain why they're thinking what they're thinking, right? And what our approach was a sample-based explanation where given a model and given a test point, I'm going to point to the influential training data points that led to the model make the prediction that it's making on this test data point. Okay, and the main way we did so was a very simple representer theorem that surprisingly was able to decompose a neural network prediction in terms of a weighted linear combination of contributions from each of the training data points. And you can talk about positive representers and negative representers, and what's most interesting are really the negative representers, inhibitory representers, which are training data points that are similar to the test data point, but would discourage the model from predicting the class that you're focusing on. And so that would give you a lot of insight as to, it looks so similar to the test image, but it does not want you to predict this class. Why is that, right? So looking at that would give you a lot of insight into the nature of that class, right? So something that looks like a dog but is not a dog gives you a lot of insight into what a dog is, right? And it's also, of course, fast to compute, very scalable, and so on. Okay, thank you.
Okay, same question.
So I was curious, with your applications, it seems that you're currently focusing on fixing data sets. I was wondering if potentially this approach, if it could maybe be used to reduce the size of data sets while maintaining the same accuracy. So maybe removing training points that are extremely similar and basically save on computational training time.
Yeah, that's actually a very interesting point, right? So, which is that if I can compute these influences, right, and then I can say that okay, here are some training data points that are never influential, or that that are too similar to these other points that are also influential, then I can then try to remove them. So using these to reduce the size of the training data set is definitely an interesting point. But of course, one will have to think about why though. So you have already trained a model on this training data set, right? So why would I need to reduce the size of the training data set? That could be still of interest in the sense that let's just say I want to allow for other people to experiment with this data set, right? And I have this gigantic data set. Then I can do this, remove the less influential training data points, and then give you a much smaller training data set that I know you will be able to succeed in fitting a very reasonable model, even though the size of the data set is less. So that could be one application in terms of communicating a data set. But yeah, that's a very good question. There is a question which people call core sets in machine learning, where this is even at the training time itself. So this is really to cut down on the training time. So if I give you a billion images you can ask this question even at training time. Is there a way for me, even before fitting the model, to look at a subset of the training data very quickly that are most influential, or I hope are most influential, and just fit my model on those. So that is a separate question. This won't be useful for that, right? So here you actually need to fit the model. But still, one can think about application.
Any other question? Yeah, so I think one follow-up question is similar to what we asked. So, is it possible to combine this approach to kind of more like they call the active learning, right? So you are trying to do some small set of training data and figure out what work for the training, what doesn't work well, and then for the remaining set of sample data, you are able to find more representative one that's maybe more likely to boost the network performance rather than put all the training data set into the training framework. So I know some math imaging people, they explore this they call the representative or so there are some kind of framework based on this kind of active learning idea. So do you think your work could be coupling to those kind of framework to have more effective training?
Right. Yeah, definitely. So, or at least the fact that there is this kernel of similarity function. So one could use the similarity function that's learned by the neural network to then talk about what are the additional training data points you should look at. So if I have a notion of similarity over the training data points, then that allows me to do active learning a little bit better. Right? Because that would allow me to quantify areas where I'm uncertain. Right? So in the sense that if there is a lot of training data points that are near to each other or close to each other in this region of space, where this notion of closeness, of course, depends on the similarity metric that's being learned by the neural network. And so in this region of the space, if there are a lot of training data points, I don't need to ask much. I have very less uncertainty. Right? But in this portion that's far away from the training data points, I have a lot of uncertainty. Then perhaps I should query there. Right? But of course, I have a certain expectation of how much I would gain in terms of information. Right? So perhaps a neural network is already confident about what that would be in that region, then perhaps I shouldn't ask that. So there is this thing about uncertainty versus the utility that I would get. Yeah, so a metric, similarity metric is definitely one component if one could think of using it. The caveat to that, of course, is that the similarity metric is not perfect. If it was, you wouldn't need additional training data points. And so there could be this issues.
Okay, any other question?
So when you use the representer structure and you simplify the number of inputs that you're getting and making it a little more normally distributed in that way, by cutting out all of the really small weights, it seems like you're getting a faster, you're getting a predictive answer, you're getting it faster using less computational time. But then it seems like kind of how we think, if we're comparing it to a brain, we have this kind of very quick thinking style, and then we have a more like engaged calculating style. And so is there any utility in putting back into the representative theorem, like the small weights, if it ran into a particularly challenging scenario where it wasn't able to quite get to the right answer? Like, is there still a utility for these like infinitesimally small weighting systems?
Right. Actually, yeah. So that's a question that we have really thought much about, which is for cases where the weights are very, very small, what is the utility of those trained data points? So if I just remove those training data points, which is again goes to the first question, perhaps I would get the same result, right? But it's a question of, would you get the same result? Is there a slight decrease in accuracy, right? But perhaps it's a very, very slight decrease in accuracy, so that perhaps you really need to carry that around for that small performance bump. Or perhaps it doesn't even affect it, right? I think this is, a reasonable question that we don't know the answer of. What are the effects of the small weights? If removing them, for instance, to create a smaller data set, how much would it affect the performance? For all we know, because of the complicatedness of these deep neural network models, they could actually improve, right? Because if I give you a lot of training data points, but many of them are kind of not that useful for you to arrive at a prediction, it can potentially confuse the deep neural network model, in the sense that it may essentially end up having the neural network model focusing on things that are irrelevant, right? Which does happen, which is that the cats are on drugs, then it'll think the drug is what is making it a cat, right? And so that's, I think, a very interesting point, which is what will happen if I just remove those. It could happen that you have this phenomenon that the performance slightly degrades, right? And that you need those to get that small delta in performance, or it could be that the performance is the same or even improves.
Okay, so if you have further questions, I think Professor Ravikumar will be here for at least half an hour. If you want to talk to him privately, you are welcome to stop by. So let's thank again for his nice talk.